Finally, we need to take a look at the stereochemistry of the E2 reaction. Remember that we looked at a picture of the transition state, and it was noted that the E2 reaction required what's called an anti-periplanar geometry between the leaving group and the base that's abstracting the proton. The reason for this is that it keeps the steric strain between the leaving group and the incoming base to a minimum. In many cases, it's not going to matter that you have to have anti-periplanar geometry. So let's look at this substrate, for example. If we look at the substrate on the previous slide as a perspective drawing, you can see that we could potentially get the base and the leaving group to be in an anti-periplanar geometry two different ways. If the base removes the green proton, you see that you end up getting a product that looks like this. And let's talk a little bit about how we orient these groups. So when we're trying to draw an elimination product, you want to keep what's on the solid wedges together. So I'm going to keep what's coming out toward me together on one side of the alkene. And then you also want to keep what's going away from you on the dashed wedges together. And so I'm going to keep these two methyl groups together on the other side. If we do the same type of exercise, but this time abstracting the red proton, you see that we get two methyl groups on the same side because here they are together. And we get a hydrogen and a methyl on the same side. It turns out that these two outcomes are exactly the same. So this was an example where the anti-periplanar geometry requirement didn't really matter. You got the same product outcome no matter if you removed the green proton or the red proton. And that's always going to be the case when you have more than one proton at the beta position, because the molecule can rotate itself into the correct orientation as long as it's a linear molecule. We are going to see that there are cases when it does matter. So for example here, we only have one proton at the beta position. So in order for this molecule to undergo E2, you have to, it has to rotate to orient the proton and the chlorine in the anti-periplanar geometry. By doing that, remember that we are putting the groups that are on the solid wedges together, so the two methyl groups over here, and then we're putting the groups that are on the dashed wedges together, so the two ethyl groups are on the other side. It turns out that you have a fixed geometry. This is the only way the elimination could have taken place. In other words, it's not going to be possible for the molecule to orient itself in such a way that you would get the ethyl and the methyl groups on the same side together. Let's take a look at how this applies to a cyclic halide. So first, let's start by identifying the alpha and the beta positions. And notice that there are beta positions in both directions this time. And let's look at which protons are eligible to undergo E2. Since they have to be able to orient themselves in an anti-periplanar fashion with the leaving group, only the trans protons on the neighboring carbons are going to work. There happens to be a trans proton on both beta carbons, but in either case, no matter which one of those you were to eliminate, you would get this E2 product. On the other hand, if we do the same thing here, we identify alpha, beta, and beta, you see that there's only one proton that would be eligible for E2 elimination, and so this carbon down here will stay the same, and this is where your double bond is going to form. Let's look at one in a chair conformation. So notice that in this chair conformation, we have the bromine here and the hydrogen here at the beta position. So here's your beta position. And these are anti-periplanar. At this beta position, you have a proton facing straight back, so that is not in the correct orientation. However, if you flip it to the other chair, you still can't get that proton in the correct orientation to undergo E2 elimination. So E2 is not possible at that position. Therefore, you only end up with one product. The only possible product will be the one shown here, where you get the elimination of the proton at this position. And if you think about it, that makes sense, because the proton that's actually back here, these are cis to one another, the bromine and this proton. It's just sometimes a little bit trickier to see that in the chair conformation.